Our first skill we're going to work on is solving linear equations in one variable. So the steps are here. There is also other ways to solve linear equations. If you know of another way that you like to use, aka a box method or anything that's not like just straight up putting it in Desmos and solving, we are solving these algebraically by hand. You're totally allowed to use those, but I'm going to show inverse operations pretty much the whole time. I'm also not going to show intermediate steps because we're beyond that. If you need to show the intermediate steps, you can. Or if everybody's like, whoa, what were those intermediate steps? I'll go back and show. But our steps are as follows. We're going to simplify by distributing. Okay, that's our first thing right here. Distributing, removing grouping symbols. Okay, removing grouping symbols, we always just called that distributing. So we're going to be distributing first if necessary. And then combining like terms, we'll collect all the variable terms on one side, and typically we like to put all the variable terms on the left and all of the constant terms on the right, just as a heads up. You'll isolate the variable and solve, and then because it's solving equations, you should always be able to check your work on these. We shouldn't get these wrong. You plug the number back into the equation and ensure that the left side is equal to the right side. So let's see an example of what that looks like. Here we are on the first example. We start off by distributing. This is 2 times x and 2 times -3, which gives you 2x minus 6. Drop down the -17. We're also going to distribute on the right-hand side this -3, so that's 13 minus 3x minus 6, making sure you distribute the negative when necessary. Then we're going to combine like terms on both sides so that the numbers just get smaller. So this is going to end up being 2x minus 23 equal to, what is that, 7 minus 3x. We move all of the x terms, all the variable terms, to the left-hand side. Just as a reminder, how do I move this minus 3x to the other side?
Plus 3x.
Cool, plus 3x, which means this becomes 5x. And how do I move -23 to the right-hand side? Plus 23 again, so 7 plus 23, that's 30. And that's what I mean by intermediate steps. I don't need to see that. I can follow along. I understand what you're doing. I obviously know you added 3x to both sides and added 23 to both sides. If you need to show that for you, do it. What's the very last step here? Divide by 5. So we'll do divide by 5 on both sides, which means x is equal to 6. Voila, we have our answer. Now, of course, we can check our work, and because we're going to be practicing in class checking our work, what we're going to do is we're going to come to the side and we're going to see what it looks like to plug those numbers back in. So we would say 2 times 6 minus 3, close parentheses, minus 17, and then 13 minus 3 times 6 plus 2. And we're just going to make sure that the left side is equal to the right side. And we're going to tune up our brains a little bit. We'll do this one by hand, but when you're working on your own, you can do this in a calculator. 6 minus 3 is 3. So I'm taking care of PEMDAS, going for my grouping symbols first. 6 plus 2 is 8. Then I'm going to multiply. 2 plus 3 is 6. -3 times 8 is -24. 6 minus 17 is -11, and 13 minus 24 is -11. Left side is equal to the right side. We're good to go. Do all those things sound familiar? Yeah, classic solving equations. Again, if you know of another method that's by hand, like not with a piece of technology, you're more than welcome to use a different method that you've learned in a previous class, but this is probably what I'm going to be showing for the majority of your course. Yes? Easy peasy. And then everybody panics when there's fractions involved. But we're not going to panic when there's fractions involved because there's one step that makes working with fractions significantly easier. They're easier to solve when we multiply each equation by the least common denominator so that all of them have a common denominator essentially, and we get rid of that denominator itself. So if I'm looking at this equation here, I have x plus 2 divided by 4 minus x minus 1 divided by 3 all equal to 2. What's the least common denominator here? 12. So what I'm going to do is I'm going to multiply all 3 pieces by 12. We have 2 minutes to lunch. So I'll show my work here so you can see what I'm doing. I'm going to take 12, and it feels illegal to do this because you're multiplying across an equal sign, but for this you can. We're going to distribute this 12 to every single fraction and whole number. okay? When I do this, it becomes 12 times x plus 2, all divided by 4, minus 12 times x minus 1, all divided by 3, equal to, almost put the wrong number, 24. We follow what's happening? Now, the reason I'm not already distributing that 12 to the x plus 2 and the x minus 1 is because that denominator is going to cancel or reduce down. Do you see how we have 12 divided by 4 right here? What is 12 divided by 4? 3. So I can just go ahead and change those coefficients to the number 3. In the second fraction, what does my coefficient become? 4. And now I have a cute little whole number to distribute instead of having a fraction to distribute, which is much nicer. And then our old skills take over. So we distribute, combine like terms, and solve for x. Distributing makes this 3x plus 6. Distributing makes this negative 4x plus 8. We combine our like terms. 3x minus 4x is negative 1x. 6 plus 8 is 14. Something's wrong.
Yeah, you put a 2.
I was about to say, I don't like where this is going. You're so right. Beep, beep, beep. Y'all stop me when I be crazy. So this is 4, which means this is 10. Okay, after lunch, we'll finish this problem up and then head on to the back page. But I'm hungry, so let's get out of here. Okay, so right before lunch, we got here, and we were just finishing up this solving equation. So we have 2 steps left. What's the step that we left off on?
Finding it.
Yeah, so we're going to subtract 10 from both sides, which means we have negative x equal to 14, and then divide by negative 1, which means x is equal to negative 14. Now again, we can check our work on this one, which means we're just plugging the number 14 in to the equation from where we started. And on these where you've adjusted for the least common denominator, make sure you're plugging in the number to the original equation without adjusting the common denominator. So we'd be plugging it in here and checking to see if that left-hand side is equal to 2. Negative 14 plus 2 is negative 16. Negative 14 minus 1 is negative 15, which means this is negative 4 plus negative 5, because minus and minus is plus. So plus 5. I think I said negative, didn't mean to. And again, did I do something wrong?
It was plus 2 to minus 2.
Where? Where did I do that?
Negative 14 plus 2.
Oh, thank you. Hee hee, I'm still on summer brain. So this makes this 12, which makes this 3. Yes, now that's 2. Okay, good. Great. Y'all got a warm-up of doing all those 4s, and I didn't do it with you, so that's why my arithmetic's a little off. Sound good? Feel good? Sounds like things we know how to do? So that's linear equations, and I know that this had fractions, so it's a little bit of an advanced linear equation, but today we're also solving rational equations. A rational equation is an equation containing one or more rational expressions with the variable appearing in one of the denominators. That's your key right here. The variable appears in at least one of the denominators. The moment there is an x in the denominator, we're working with rationals, which means we have a bit of additional rules going on. Because you cannot divide by 0, we have to make sure that we're looking at these two terms here to see what would make those denominators equal to 0. And we're going to add that restriction to our answer, meaning we're going to take some numbers out of the real number line and say it can't be that one and it can't be that one. So in this case right here, since x is in the denominator, that just simply means that x cannot equal 0. Any other number is a potential for what could be a solution to this, but we know right away that 0 cannot be an answer. If it does become an answer, it's an extraneous solution because we can't actually use it. But otherwise, the steps are exactly the same for what we did just a second ago. We're going to find the least common denominator, and we're going to multiply each of the terms by that so that we end up with a linear equation without fractions. So even though there's numbers down here, what is the least common denominator between x, 5, and 2x? 10. X, yes. So X's can be included now in our greatest common, or least common denominator. So we're going to multiply each and every term by 10x. And again, this is the part that looks kind of funky because it feels like you've never been allowed to do this, multiplying across an equal sign, and you really haven't until you're doing something like this, multiplying by the scalar, and I missed a whole x, 10x. But when we distribute this to all three terms, here's what it turns into. This becomes 10x over x, 10x over 5, 30x over 2x. We follow? Bless you. You're welcome. And then we divide. Last time when we did this, the constants or the coefficients canceled out. But for this one, we're going to get a bit of a cancellation from some of our variables. This x and this x cancel each other out, which means this first term is just 10. In the second one, the 10 and the 5 reduce down to the number 2. And in the last one, 30 divided by 2 is 15, but the x's cancel each other out again. And that's what I'm left with, which is much easier to solve for. Subtract 15 from both sides, divide by 2, so negative 5 over 2 is the solution. Are we following along here when I'm skipping these intermediate steps? Yeah, adding or subtracting and then dividing is what I'm doing in those. I'm just not showing you what I'm doing. Now, when we're doing a rational function, it is actually very important that you check your work, not just to make sure you get the question right, but we need to make sure, especially when we get to harder problems, that we haven't accidentally broken this equation and picked something that was a part of the restriction. So we are going to check our work here, because I also want to review some fraction rules with you. If we plug this in, this is going to be 1 over negative 5 halves equal to 1/5 plus 3 over 2 times negative 5 halves. All right, let's go over some fraction rules. Do we know the rule for dividing by a fraction? Keep, change, flip. Yes. So you keep the numerator the same. You change the divide to a multiply, and you flip the fraction in the denominator. Keep, change, flip. So that actually becomes really easy. It's just 1 times negative 2/5, which I'm just going to erase this 1 times. It's negative 2/5 equal to 1/5 plus 3 over something. Before we keep, change, flip that, what's the rule on multiplying fractions? Do we remember? You can say no if you don't remember. Top times top, bottom times bottom. So yeah, so we do 2 over 1 so that we see a top and a bottom for both. So it's negative 5 times 2, which is negative 10. Oops, this should still be in the denominator. This is negative 10 over 2 times 1, which is 2. And then what is negative 10 over 2? Negative 5. So we can just make that negative 5. So much easier. Now the way I've written this actually makes this kind of confusing. Let me write them all as fractions looking the same so it's not sideways. This is negative 3/5. What is 1/5 minus 3/5? Negative 2/5. So we're good. We checked our work. All right. Let's try the next one, because that's a single term, that's fine, but what if there's a binomial in the denominator, so a 2-termed expression in the denominator? We're still going to treat this the same, and we're going to find the least common denominator. Right now, the 9 has a denominator of 1, just to help us remember that, because every whole number does have a denominator of 1. What is the least common denominator here? X minus 3. So that is what we're going to multiply every single term by. Okay, I'm not going to show that step where I distribute. I'm just going to go ahead and do it. So the first one would be x times x minus 3 over x minus 3. The next one would be 3 times x minus 3 over x minus 3. And the last one would be 9 times x minus 3 over 1. And I'm just putting the over 1 so you see what I did there. See how each term got multiplied by that least common denominator? It's exactly what we did in the other problems. This one's just a binomial, so it looks a little different. What happens here?
Oh, they cancel.
They cancel. We don't even need to distribute because look, these cancel out. What happens in the second fraction? They cancel out. What should I do in the third fraction? Yeah, this is where your distribution is going to come in. Because it's over 1, so like, bleh. This means we end up with x is equal to 3 plus 9x minus 27. And we go back to solving like normal. I'm going to move all the x terms to the left-hand side, which means I'm subtracting 9 from both sides. And I'm going to combine the constants. They're on the same side, so it's not like I changed the signs at all. 3 plus negative 27 is negative 24. Divide by negative 8. Negative 24 divided by negative 8 is 3. Voila, we found our answer. Now again, this is a rational function, so we have to check our work. When I'm plugging this in, it would be 3 over 3 minus 3 equal to 3 over 3 minus 3. I hope your spidey senses are tingling right now. What's wrong with this right here? 0. Are you allowed to divide by 0? No, we did this last class if you got to the slope ones. What is it called? What do you say when you try to divide by 0? Is undefined. So here's a problem, and hopefully your spidey senses are going off like, okay, well, we have an issue because we just broke this function when we tried to plug in what we had. Why is that? Why does the solution we got correctly not actually work? There is no real solutions, correct, but particularly why does the number 3 break this function? What number would make those denominators 0? 3. So from the jump, and here's why you check your work, because in case you forget to check for your restrictions at the beginning, we know from the very, very beginning of this problem that x is not allowed to equal 3. That comes from the fact that x minus 3 is in the denominator. So since we solved this equation and we got 3, we'd have to throw this away. We'd say, never mind, this is extraneous, and we have no solution for this function. Now, being that we have no solution, we're going to introduce a new symbol for what you can write for no solution, because your textbook likes to whip that out every once in a while and talk about a different way to say no solution, and that's going to be on your next page. The first two definitions here on types of equations make a lot of sense. You've seen a lot of them before, maybe not called these things, but you know what it is. On this side right here, I'm not looking at the definition first. If you were to add these two numbers together, wouldn't this equation end up being x plus 3 equals x plus 3 on both sides? Yeah, that's true literally at all times. Whatever number you plug in, plus 3 is going to equal the same number plus 3. That's called an identity. So when your answer would be all real numbers, that's technically called an identity function. Your textbook uses set builder notation to talk about this. In previous classes, you probably would have used this fun and funky R to talk about all real numbers. I'm personally okay with both as long as you know the textbook probably wants the word definition or the set builder definition. The second one is what 99% of equations are. This is what you're used to solving for. It's called a conditional equation. This is an equation that has one solution, okay? When you can actually solve an equation and get a solution, that is technically called a conditional equation, because it's only true if x is equal to 7, or only true if x is equal to 0. That's 99% of equations that you see. The last one is what we just witnessed on the other page that's called an inconsistent equation. An inconsistent equation is an equation that is not true for any number whatsoever. This is what you would have called no solution before today. Now we call it, I pressed the wrong button. Now we're going to use this symbol that's called the empty set. Okay? Now there's something to be very clear about here. That symbol is not 0. That symbol is not theta. So if you have taken a trig class before, that is not theta. Here's the difference. This is 0. This is theta. This is the empty set. I spelled that wrong. Empty set. What is the difference between those three symbols that I've just written up there? The line. For the 0, does it extend past the 0 itself? No. For the theta, it's sideways and does extend past the circle for the 0. An empty set for sure extends past and is diagonal. So for me, if you write zeros with lines through them, that's fine. Just make sure it actually is a 0 and not the symbol for the empty set. Now that we know that that is the symbol for the empty set, that means no solution. Okay, so that's a button on your textbook. Whenever we get the online homework, it will be a button that you click for the empty set, and it looks like that symbol. Yes? Okay, cool. So when we're solving to determine what kind of equation you have, whether it's an identity, a conditional, or an inconsistent equation, you're going to want to solve it down as much as possible. If you eliminate all of the variables, it is either an identity or an inconsistent equation, because then you're going to have to determine if it's true or false. What I mean by that is, for this problem, when we're going to determine whether it's an identity, conditional, or inconsistent equation, we're going to solve. So we distribute first, and boom. We're going to eliminate move all of our variables to the same side, which is subtracting 2x from both sides. But when you subtract 2x from both sides, all I'm left with is 2 equal to 3. Is that true? No, like literally 2 does not equal 3. So that's a false statement, which tells us that this is an inconsistent equation. And we would answer that the solution is the empty set, which is the 0 with the aggressively long line going diagonally through it. Inconsistent equation. If we try that again with the second equation here on the page, again, we'll start by distributing on the right-hand side, which makes that 6x plus 6 minus 2x. Combine like terms on the left-hand side. And hopefully your spidey senses are going off. What are you noticing already? It's the same on both sides. So technically, if we go a step further and eliminate your variables, so minus 4x, you end up with an equation that says 6 equals 6. Is that true? Yeah, 6 is equal to 6. So that's a true mathematical statement, which, yes, does mean that this is an identity equation, meaning all real numbers are your solution. For me, I don't mind you writing the all real numbers symbol, but your textbook uses the set notation x such that x is a real number. Questions, comments, concerns? All these things sound familiar, right? We've heard all of these things at some point in our mathematical career. Cool. Last thing for today is truly the application of equations comes from different things. We're not just going to sit and solve equations for the rest of our life, especially because this is the stats version of this class. We will see a lot of graphs in the spring, and we'll have to be able to read graphs and understand what it's telling us. So this question says, studies have shown that people with a low sense of humor have a higher levels of depression in response to negative life events than those with a high sense of humor. These graphs can be modeled by the following formulas. We see the graph, we see the formulas for people with low humor and high humor. If we're reading our graph, this is the intensity of a negative life event along your x-axis, and this is your group's average level of depression in response to negative life events. Okay? In each formula, x represents the intensity of a negative life event, that's our x-axis, yeah, and d is the average level of depression in response to that event. The question is, if the high humor group averages a level of depression of 3.5 or 7 halves in response to a negative life event, what is the intensity of that event? And what does that solution look like on the graph? So we're using the high humor group, right? So that means we're going to use this equation here. And it tells us that their level of depression is 7/2. Did they give us X or did they give us D? D. So when I'm solving this, I'm going to say 7/2 in the place of D over 1/9, or equal to 1/9 X plus 26/9. And I'm going to need to solve for X. Okay. Is this a rational or a linear equation? Is there an X in a denominator? Where is the X in this equation? Is it down low or is it just like to the side? To the side means that it's linear. It will be straight up in the denominator if it's rational. So if you're looking for a hint of what to do, you can flip back to the linear page, the front page of these notes. But what we did to solve these when there were fractions involved is we got rid of the fractions pretty quick. What did we multiply the whole thing by when we were solving these? The least common denominator. So what is the least common denominator here? 18. We're going to multiply every single term by 18. So 7 times 18 is 126, just to fast forward. 1 times 18 is 18. And 26 times 18 is 468. I hope you trust me that I put those in a calculator correctly. I mean, what? I did it in my brain. I'm so smart. Not. Okay. Then we divide. 126 divided by 2 is 63. 18 divided by 9 is 2. And if you trust me, 468 divided by 9 is 52. Right? We can all type things in a calculator. We're just going to fast forward past that part. Then we're solving. Subtract 52 from both sides. That's 11. Divide by 2 on both sides. That's 11/2 equal to X. So we would say that the intensity of the life event that these people had was a 5.5 on this scale. Now the answer is the first part. Second part of this question says, how is that solution shown on the red line graph? I'll zoom back down if you didn't get all of that just yet. But if I'm looking at this this graph right here, and I find 5.5, which is about here, does that kind of correlate-ish to 3.5? If I look at that coordinate point, that would be right here where X is 5.5. Is my output 3.5? Yeah, that's pretty good. So that means that our coordinate point on the red line graph would be the coordinate point 5.5, comma, 3.5. So these graphs and these equations are working together. Solving an equation is the same as reading a graph, if your graph is easy to read.